So for capacitors, what's the relationship among power, energy, and the charge on them? One of the first formulas that you learned was that power is equal to voltage times current. That's one that you should definitely have devoted brain cells to memorizing a long time ago, because it's true for any electrical component. From physics, you know that work, or energy, is the integral of power, which means for a capacitor, it's the integral of voltage times time, dt. But from our previous page, we know that current is equal to capacitance times the derivative of voltage with respect to t. We know that this value is the same as that value. So now doing some fractional cancellations that my calculus teacher would have found abhorrent, but which I can do since he's not here right now, is I can cancel out those dt belows and dt above, and I can take that capacitance, which is a constant outside the integral sign, and so I can show that the energy stored on that capacitor is just equal to capacitance times integral of voltage dV. Now we're almost there. The integral of V dV we know is equal to 1/2 V squared. So, writing it in the more typical way that you'll find it, the energy stored on a capacitor is equal to 1/2 CV squared. And that's important enough that even though you could derive it as I just did, you want to give some brain cells to it. So remember, that is the energy stored in a capacitor. The last relationship is one that you should just know, and that is the charge that's pushed into one side of a capacitor and that flows out the other side. That charge differential is equal to the capacitance value times the voltage on that capacitor. I hate to give you lots of things to use brain cells on, but these are all important examples. So using the intuitive hydrodynamic analogy, what we're saying is that Q is plus Q here minus Q here of charge. Q is like your gallons. V is the voltage difference between the top of the bent diaphragm and the bottom of the bent diaphragm. And C is like the floppiness of that capacitor. So for a given voltage difference, if you make the capacitance really floppy, you've stored a whole lot more charge, which again intuitively makes sense. The last concept in this slide is how capacitors act in their DC steady state. So you've got a steady state, which means unchanging DC input. And if that's true, then capacitors, you can draw them as opens. And the voltage across that capacitor, if you could truly draw it as an open, has to be the voltage across the open. So let's give an example. A 12-volt source, 4 ohms up here. We've got an 8-ohm shunt. There's a 2 microfarad capacitor, and we want to find both the voltage across that capacitor and we want to find the current through that capacitor. So the first step is to realize that this is DC steady state. There's nothing that's changing in it. There's no cosines or sines. All the voltages have to be constant. And because the voltages are constant, we can redraw that capacitor as an open. It doesn't matter what that capacitance was. everything else has to be the same if it's a valid model. And now we can derive what these are. Now, if there's no current flowing through it, then the only place current can flow is around here. The amount of current that flows in that circle, we'll call that current I, is going to be equal to 12 volts divided by 4 plus 8 ohms. That's the total amount of resistance that this closed pathway sees. So that's going to be equal to 1 amp. So 1 amp flows there. How much current flows around here? Well, as much current as flows through any open, which is 0. So by inspection, there can be no current that flows through this open, so IC is equal to 0. Does that mean if there's no current that the voltage has to be 0? No. After all, let's say that you were given, let's say you were handed a battery, an AA battery, and it's a 1.5 volt battery. If I just handed it to you, there's no current flowing. Does that necessarily mean that it's not a 1.5 volt battery? No, of course it's a 1.5 volt battery. It has no current flowing. There's no problems with it. So the fact that we know that there's no current does not mean VC is 0. What it does mean is that VC has to be this voltage here, because it's connected by a wire, has to be the same as that voltage here, which has to be the same as this voltage here. So the voltage across the capacitor is the same as the voltage across this 8 ohm resistor. What is it? There's a number of ways to find out what it is. One way is to say if VC is the same as the voltage across the 8 ohm resistor, by Ohm's law, which we can use since it's a resistor, that has to be equal to the current through it times its resistance. And we know that we just said from up here is 1 amp flowing through it times 8 ohms or 8 volts. So therefore VC is equal to 8 volts. And those are the answers to the problem. Now, if you were clever, you could see that in fact you didn't need any of this. In fact, you could have solved it in one step. By inspection, no current flows through the open, so IC is 0. Second, by inspection, the voltage across the capacitor is the same as the voltage across the 8 ohms. This circuit to the left is a voltage divider, so VC is equal to V8 is equal to the voltage source times the voltage divider relationship, which is 8 over the total resistance, and that is also 12 plus 8 over 12, which has to be also our 8 volts. And we get the same answer either way. One using finding current first and then finding voltage, and the other way going directly with a voltage divider. And so in summary, when you're analyzing DC steady-state behavior of capacitors, nothing's changing. There's no switches. There's no changes in voltages. There's no functions of voltages happening. The way to analyze it is to replace the capacitors with opens, and then the rest of the circuit just becomes a circuits 1 problem.